So I just want to start this video with summarizing the x is small, or I'm sorry, not the x is small, I'm getting ahead of myself, sorry. We're going to summarize K, and this is true for both KC and KP. If you remember from the last video, KC has to do with concentrations, KP has to do with pressures. So here's your summary. When X, I'm still going with X is small. I just doctored up all the slides again. Sorry, guys. When K is very, very small, and we think about that as a factor, a magnitude of 10 to the minus 4 or greater, the reverse reaction is what is favorable. If K is very, very large, again, a magnitude of 4, 10 to the 4 plus, very large, the forward reaction is favorable. When K is approximately equal to 1, neither the forward nor the reverse reaction is favorable. They'll pretty much go back and forth equally. And then you have your relationship between the KP and KC, where KP is equal to KC times RT taken to the delta N power, where N is the difference between the moles of the products and the reactants. So here's where I inserted some slides that are not on your original PowerPoints, but I can upload this PowerPoint as a secondary thing if you would like to print it out. So when we do these mathematical calculations, I'm going to clarify again about the X is small approximation. Generally speaking, we only use the X is small approximation if we know that K is very, very large or K is very, very small. That means you're going to assume roughly 100% is going to be in the forward or reverse reaction. And we assume this based on K. Then we'll do the ICE table like you've seen in the previous examples, solve for X in the ICE table, assuming X is really small, and if X is in the bottom of the fraction when you're dividing. I'm going to show an example in just a second. So here's an example I have. If you had this equation right here, and you know it's Kc, this Kc in this particular case is very small. It's 10 to the minus 12 power. That's an exceptionally small number. I'm telling you that for this just generic example, the initial concentration of the iodine is 0.45 molar. So we set up our ICE table, and we know that we're starting off with 0.54 molar of the I2 gas, and we start off initially with 0 product. The change here will be subtraction of some X, because we don't know what it is, and the increase of some change by 2X, and it's 2X because the coefficient from the balanced chemical equation is 2. Then at equilibrium, we can make this statement. So at equilibrium, the concentration of I2 will be 0.45 minus some change, minus some X. And the concentration at equilibrium of the iodine ion will be 2X. So in order to solve for this, we have to set up our products over reactants Kc equation, which you see up here. So we have Kc is equal to the concentration of I squared. It is squared, again, because of the coefficient from the balanced chemical equation, divided by the concentration of I2. Okay, so we plug and chug. We take the 2X, put it into the term. We take the 0.45 minus X, put it into the term. And now we're going to make that X is small approximation. We've assumed that X is so small that it's negligible to the numbers we're dealing with. So here's the example I give for that. If you stand on a digital scale holding 1 penny, okay, if you were to throw that penny away, still standing on the scale, is your weight, the number on the digital scale, is that going to change because you put the penny down? The answer is no. The mass of the penny is so negligible to the total mass on that scale, it's not going to be read. You'd have to have a scale that went out to probably 10 decimal points in order for you to see a change. So the idea is that mathematically, X is so small, we can ignore it in the bottom of the fraction. You cannot ignore it up here, okay? Now, so we rewrite. We know Kc because it was given in the problem. We now solve for x here. And if I rearrange to solve for x, it would be the square root of this number, which I got by multiplying 0.45 by 5.6 times 10 to the minus 12, divided by 4, because that squared applies to everything, right? The x squared and 2 squared is 4. And if I do the math, you're going to get 7.9 times 10 to the minus 7 molar. Now that's just solving for x. Remember, if you had actually had to find the amount at equilibrium, you would go ahead and plug this number into these two terms here to solve. I left that part out of this example because that's not what we're working on. So you always have to check and say, you know what, did this really work? Am I okay with making this approximation? Because it doesn't always work. And when it doesn't always work, you're going to have to use the quadratic equation. I recommend programming that quadratic equation into your TI scientific graphing calculators if you don't already have it there. So the rule is to make the x small approximation, when you go back and check after you've done the math and assumed it's small and gotten rid of it, you have to say, okay, let's just double check. What this means is that the x that you solved for divided by the initial concentration times 100% must be less than 5%. If you're less than 5%, you're golden, you're good, you can keep your numbers. If it's greater than 5%, you're going to have to go back and rework the math using the quadratic equation, okay? Now, I take my x that I solved for, which was 7.9 times 10 to the minus 7, divided by my initial concentration, which is 0.45, multiplied it by 100%, and I get 1.75 times 10 to the minus 4%. That is clearly significantly less than 5%, so I am good. I am good with using this x small approximation. Now we're going to get into the reaction quotient. The reaction quotient is going to be related to K. K gives us our concentrations at equilibrium. Q gives us our concentrations at any point that is not at equilibrium. Okay, so it's kind of an instantaneous concentration. So to calculate Q, we're basically doing it the same way we do for K, products over reactants, taking into account their stoichiometric coefficients brought up to that power. So if Q equals K, then the system is at equilibrium. All right. If Q is greater than K, there is too much product, and therefore the reaction will shift to the left, back to the reactant side. If Q is less than K, there's too much reactant, and the equilibrium will shift back to the right, back to the product side. We'll talk about shifting in just a second. So here's our summary. If Q is greater than K, shift left towards the reactant side. Q equal to K, no shift, we're at equilibrium. And Q less than K, shift right off to the product side. So I told you we talked about this shifting thing. What am I talking about? What does this shifting stuff really mean? LeChatlier's principle, that's what it means. LeChatlier was a guy, French guy obviously, who came up with this concept and figured out that when there's any disturbance to a system at equilibrium, it will shift in order to get back to a new equilibrium. So here's the principle. If a system is at equilibrium, it is disturbed. If a system at equilibrium is disturbed by a change in temperature, pressure, or concentration of the components, the system will shift its equilibrium position so as to counteract the effect of the disturbance. Now, when it shifts back to equilibrium, I use the term back loosely. It's not really shifting back to where it was. It is shifting to an equilibrium, but now we're at a new, different equilibrium. So here's an example, the Haber process. We can take nitrogen gas and hydrogen gas and form ammonia, all right? Now, when we do this, depending on what's happening, you're going to get a different amount of product in the end. So if I have pretty low temperature, pretty low pressure, but pretty high temperature, you're only looking at 38.7% of product being formed. But if I increase my temperature and pressure, so I'm at the peak pressure, peak temperature, this is where I'm going to get my largest product produced. If I were to shift anything here, if I were to drop the temperature, you could see the product would drop. If I were to drop the pressure, you can see the product formation would drop. Okay, so every shift that occurs, there's going to be a shift in the dynamic equilibrium. So let's just talk about this in terms of shifting left, shifting right, et cetera, et cetera, et cetera. Okay, if we were to say, okay, this picture right here, that the first with the test tube in the beaker where we have this kind of purpley color, that's at equilibrium. There's enough amounts of both blue and pink to make our pretty purple color. Okay, they're about even. The concentrations are about even. So this is an endothermic reaction. If it's endothermic, that means you're going to treat heat like a reactant. If this were an exothermic reaction, we would treat heat like a product and actually write heat on the product side of the reaction. Okay? Now, if I were to increase the heat, here is what we would get. We'd get more blue. If I were to increase this heat, it goes up. When I increase the heat, the reaction will shift to the left in order to form more products. All right, here's my generic, silly example about how this works. Let's say I start off with 2 pizzas and 4 people. Okay, now, as the 4 people are consuming the pizza goes away. Well, as the pizza goes away and I'm still hungry, I'm going to bring in and increase more pizza. But then maybe I bring in more people. So now there's a rush to increase the amount of pizza I have on hand. Oh, but then people go away and now I have too much pizza. I don't want leftovers because it's not going to fit in my fridge. So the people are going to have to eat it up to get rid of that pizza. And the whole idea is we're good and done when we're at the point when everybody is full and there's no pizza left. Okay? This kind of ebb and flow of changing a product to get changing a reactant to get a product, changing a product to go back to the reactant side. It's just this ebb and flow shift. So if I, for example, in this, if I increased the amount of the chloride ion here, the reaction would shift to the product side because I'd have too much chloride ion. They'd have to make more product. But if I decreased, say, for example, this product right here, if I decrease this, then this side, the reactant side, would rush to make more product to get back to a new equilibrium. Because at equilibrium, this pretty purple color here, that means everything is about the same concentration. This is endothermic. So if I decrease the heat, if I take away the heat, the reverse reaction is going to shift to the left to form. Okay? Catalysts, they increase the rate of reaction. They do so by, 1, lowering the energy of activation. They also do it by increasing the rate at which the reactants can, interact and therefore form products. What it does is it will increase both the rate of the forward and reverse reactions in these chemical reactions. All right, so the ratio will stay the same, but the rate at which it gets to become at equilibrium is increased by use of a catalyst. So generally, when we use a catalyst, we get the equilibrium faster, but the concentrations would still be the same whether or not we used a catalyst. Okay, so that's it for the second half of chapter 15 on equilibrium. Make sure you print out the equilibrium worksheets that I uploaded and bring them to class on Tuesday. And that's what we're going to work on Tuesday. So I understand this was kind of a lot, this chapter's a lot of information, but this is why I want to work the problems and worry less about lecturing in class and work problems in class so you can get the hang of this like we did last week. If you have any questions, please let me know, and I will see you guys Tuesday. Have a good rest of your weekend.